two variants of it.
I had a question on the
yes, please go ahead.
Yeah, is this the minimized learned clause? I'm not sure I got, I mean, is it the same as asserting clause?
Yes, exactly. This is an asserting clause.
So you have a different name for it. I hadn't
no, the
heard reference to this. Oh, okay. So this is the first time. Yeah. So, okay. Got it.
But this is also asserting clause, by the way. And also the this other one, this bad one, is also asserting clause. They're all asserting clauses. So asserting clause is one where you have this property that it only has one literal of the last decision level and otherwise cuts the conflict from the decisions.
Yeah, but an asserting clause always has the UIP, correct?
No, asserting clause are all of them. Like
the one with the UIP or the first UIP would be.
Yeah, this is called first UIP clause. So I wrote it somewhere. Yeah, here you see this is the. Sorry. This is the first UIP clause, right? That's how you call it, and then you minimize it, and that would be then the. Well, this is locally minimized, where you only sort of like resolve away literals, which this one here, which are already so where its antecedents are already in the learned clause, okay, and then you can do this non-local recursive minimization, and then you get sort of this recursively minimized learned clause, and this guy is also an asserting clause, but also the one I just marked here. This I need to get my thing again. So this one here is also an asserting clause. They're all asserting clauses. And you could all use all of them. So CDCL would work with all of them. It's just like that this, first of all, you should do really this first UIP clause, and also from the recursively minimized one, you get an additional edge. So that's like the one you should do. Okay. Then let me point out there was a paper, this SAT conference by a student of Fahim Bacchus, Nick Feng, who went back to the idea to check whether it also makes sense on previous decision levels, like maybe on this one, really try to get a UIP without, that's the important part, without pulling in additional levels, right? Remember when we resolve away the S here, we will pull in decision level 3, what we should not do. And you could also on lower decision levels do remove additional, sort of shrink the clause by adding new, by replacing parts of the clause by just a single literal, but you only should do this if you don't pull additional little levels like this level 3. And yeah, I ported this to KISSAT and it actually works. And I will port this also to Caticle back, like a separate implementation of Nick Feng's implementation. But if you want to know more about that, so just read his paper from the SAT conference. There's also video, I think, which you can also watch the video. Okay.
What is the name again of the student? I'm sorry, that you talked about?
Nick Feng and Fahim Bacchus. Two Z's.
Thank you.
20. And it's called All UIP. That version actually won the Perlanning track. When okay.
Excuse me, can I have a question? So
yes, sure.
Process, is there when you go back, is there some non-determinism when you walk back?
No, this is a unique thing, and the non-determinant, yeah, there's actually some papers on this, so that's a good point. Ellen van Gelder has a paper in 2009. So the non-determinism comes from the following fact. So when you restrict it to the clauses which are in the implication graph, right, which are kind of implicitly here, then it's a unique solution. And the reason for that, so there's like one minimal and one unique one. And that's, and the cool thing is if you look at these implementations, which I haven't described how this really is implemented, it really makes use of a lot of sort of like features, like things which invariants which hold in the SAT over. Particularly, you need to resolve these to find this first UIP. You actually need to find an articulation point. So these unique implication points are articulation points. Maybe you know these from graph theory. These are sort of nodes in the graph, which if you remove it, split the graph into disconnected components. And actually, to find such things, there's like an algorithm by Tarjan doing that, and it's related to topological sorting. So if you know I have a topological sorting of the graph, you can easily find these unique implication points by simply counting how many kind of open paths you do have. And we do have in the topological sorting of the literals, because all these arrows here, they can only go from literals which are earlier on the trail on this assignment stack, which were assigned earlier. So T was assigned before, or T was assigned before Y, because otherwise you would not have this reason here. So you have a topological sorting, and then you just go backward in this topological sorting, and you count how many literals are there on the current decision level, and that if this number drops to 1, you find the first UIP. And that's beautiful. So very simple implementation. This is not true anymore for this paper here. There you really need to do a little bit more. And the way you do it is, and I also do it, is you're using a priority queue where you put in the trail height as a score, and then you always take out the literal which is the largest trail to get this topological sorting. But then it's not linear anymore. It would be sort of n log n because of the priority queue, but it's still doable. And okay, so this keeps it all deterministic. This what I just described are just implementation tricks to do that. And if you want, this is one part we could look at later in the code section. Now, of course, and actually figured this out in 2009 when Precosat, when I implemented Precosat, and many other people had the similar sort of idea. There might be different ways to derive the T, right? So it might be the case that H and L imply T, okay? There might be a clause which says not L and not H or T. And therefore, you could also use that clause to for this minimization. And actually, it's easy to implement. So in these minimization algorithms, when you go sort of backward in this topological order, you always pick the reason. But what you could also do, you just go, you're iterating over all the possible reasons. And the nice thing is that these watch data structures actually allow to find you all potential reasons, because reasons which you can use here are clauses which are unit, right? So everything is false except for one literal. So all these clauses are watched, like this alternative here, which would be not H and not L or T. That's a clause that's currently watched for T. So that means I could go, when I go over all the watched lit clauses here for T, and I just figure out whether these clauses are unit for T. And if so, I can use this as an alternative. And it's also simply a linear graph search to do so. But then it becomes non-deterministic. And it's even worse. There's a paper also from 2009 by Ellen van Gelder, which shows that using all these potential other reasons can give you a shorter clause, but it's NP hard to find that one. I think this answers your question, right? Oops, sorry, wrong. So after we're done with after we're done with the decision heuristics and sorry, after we're done with implication graph and also looked at encoding. Then I want to talk about decision heuristic, which is really the one of the most important parts here in solvers. And I think you probably know this VSITs, and I want to point out here this survey which talks about this part. So I want to go faster here, but if you're interested, I can explain more later. So in particular, in that paper, we also implemented variable move to front actually in that paper here. And this was invented actually by Ryan. So I mentioned Ryan before. His master thesis was the one which coined the term conflict-driven clause learning, and it was his Solver Siege, which he actually sold to industry, and that's why we don't have the source code of this thing. But binaries we still have. And basically, so I'll show it simply on the next slide, then you will see what's going on. Instead of these VSITs, which you should all familiar with, so I will not explain that, variable move to front has a much simpler idea. It would keep the variables here, like in a list, in a doubly linked list, like here. So like there's variable 5, 3, and 4, and 9, and 7. And let's assume we also have the values of these variables current to which they are assigned here. And like you see here is an unassigned. So 0 means assigned to false and 1 means assigned to true. And then what's this last number? So this is kind of the trick I invented back then in 2015. This trick, this number here gives you when did you sort of put this variable on this queue, right? So that's why this is a topological, a number which increases when you go to the right of the queue. And now what does variable move to front do? Well, first of all, you start here at the right and you try to find the best, the first not assigned variable. So, and for that we have a cache here, which is this next search here, which tells you, oh, I've searched already these guys. So I searched already like 7, 9, 4, and they're all assigned. But then I maybe found 3. And 3, I picked 3 as decision and assigned it to 1. So that's why I keep this next search cache here at this variable. But now during backtracking, it might be the case that, all right, 9 gets unassigned, okay, because I'm backjumping or whatever. And then during the backtracking, I need to fix this next search pointer, right? Because the invariant of this data structure is that right to this next search cache, there's no unassigned variable. But then what I simply do is I unassign 9, and at the point when I unassign it, like here, I check its time when it was put on the queue and check whether the next search variable, this one, has a smaller time. And if so, I just update this next search to this next search prime. And therefore, like in constant time, I'm able to update sort of this next search thing. And then this explains like unassigned, and the other operation you need to maintain this data structure is bumping. So bumping is like in VSITs, remember you add this increment to the score of a variable. So here bumping means actually, and this is the idea of this variable move to front, you have like your queue, like these are your variables, and then maybe my 2 thumbs are variables which are in the conflict and need to be bumped, so they're taken out and they're moved to the right. Okay. So in this case, for instance, 4 is bumped. Like this is this literal here occurred in the resolution of the learned clause, and therefore it's bumped. So it's put to the end of the queue. And maybe I did this on purpose. Remember from the discussion we just had, this value of this variable will be false because the learned clauses and everything we resolved has kind of false. But of course, like these are variables, not literals. It's just like coincidence that it's false. But nevertheless, so these literals are false corresponding to this variable, and so it needs to be taken out. Okay, so I'll get the list bucket of this variable, which is indexed through an array. And I need to update these pointers here. that's easy, right? So it's just like cut these pointers, go back forward, concatenate it to this one. Oh, I should do this with my, so the bumping would sort of cross out this guy and do this one and this one. This is easy. And now the new thing is, because I need to update the time here. And well, it's just like a global counter. And this way I still maintain this invariant that everything right to next search is unassigned. And these times here are all in increasing order. Okay, and with this trick, actually you can implement variable move to front. When Ryan did this in 2004, he had to restrict it heavily. So he only did it for very short clauses. And so it didn't really work. And only with this trick, with the timestamp here, you can really make this fast. And it's actually faster than the binary heap, which is used in the ordinary VSITs implementation. All right, now also in that paper from 2015, I have like lots of different ways. And I don't explain this, but sort of what everybody's implementing is the idea of the two Niklas, which I would call exponential VSITs. In the original one, they actually really sort of halved the score every 256 conflicts. So that's why it's kind of strange here. You can normalize VSITs to 1, and then this almost looks like an exponential moving average, or some people would call it reinforcement learning. And I can elaborate on this if you want, but this will take some time. So I want to show here that is like there's this variable move to front, and there's this exponential moving VSITs. These are the two, which actually this one below and this one, which are these implemented sort of in my solvers, and which I recommend to implement. Actually, want to implement a very simple solver, you should really implement here this variable move to front for several reasons. One reason is that a standard priority queue you can get from STL or from some other container class would not have an update function. So you need like additional libraries to do this. So you would need to implement your own container, like in the Minisat solvers. While variable move to front, you can just it's far less code to implement. Okay, this gets me. Yes, please.
Sorry, I guess this is maybe a bit advanced, but I think it might be also interesting, perhaps also for others. What I've observed is that, for example, with BMTF, we get significantly better cache usage. I'm expecting this to be because of, not because of the order heap, which, as you mentioned, also is expensive to maintain in other scenarios, and in BMTF you don't have this overhead, but that sort of accounts for about 20% of the time gained. But to me it turned out that the speed advantage was much higher than 20%, and yeah, so okay, that's good that you confirm it. And it felt to me that it was, my guess was, maybe I'm wrong, and you can tell me, but my guess was that because of the cache usage was much better with this BMTF, which to me sounds like we're doing a much more local, quote unquote local search, and that's why the cache usage is better, because you keep on using the same clauses, and of course then you don't have to pull them from memory, and which is very expensive, as everybody I guess knows from computer science, that reaching out to memory and storage that is further away or cache that is further away is always a lot slower.
Yeah. Let me reiterate. Good that you ask it. So there's like a couple of follow-ups on that I would have actually mentioned. So first one is what you just said. So when I said 20%, this was misleading. I meant like usually the time spent with profiling in just decision heuristics, which is like finding the best variable and also bumping it, is currently 30% roughly, if you use a binary heap like in Minisat or in Maple. While if you do this VMTF, it goes down below 10%. So this difference is 20%, but of course you're right. The difference, like total time between the two, is more like a factor 3, 4, 5 or so between the two. So this is way faster to do. However, it changes the heuristic, so it's not the same, and that's what would have been the second comment. And if you want to get an intuition about this variable move to front, it's really just how caches work. So it's like maybe this idea of online algorithms and this variable move to front, actually, yeah, maybe I should switch to my whiteboard. Everybody knows that if you're sort of have a linked list, right? So like 7, and you have an algorithm. Now I put 0 just for sake, and the algorithm has get minimum. Okay, get min.
You're presenting the slides, Amir, and Armin. You're not presenting your whiteboard. You might need to switch that.
Ah, thanks. Though I need to stop the. There's the stop share. Just a second, and share again. And I need to share this desktop. Okay, that's what I wanted to do. Do you see the whiteboard?
Yeah.
Okay. Yeah. Right. So this is a linked, simply linked list. Actually, you can even do it one link. Okay. And you want to have an online algorithm which does get min, and of course you want to push something. You put if you have one single list, you would put here, for instance, a 4. But you don't keep things sorted, right? How can this be fast? Okay, and one way of doing this is you go through this list and you find you always swap the minimum to the front, and that's very similar to this variable move to front. Anyhow, so this is not elaborated, so I just wanted to say that. So maybe there's some, but we can discuss this later. All right. At least the similar situation is here. So you're really kind of having a much more local data structure than this a binary heap. So usually you would use a binary heap for these visits, and these binary heaps, they have not good hash behavior because you always have to bubble things up. So if there's one trick by Niklas, actually also Sørensen figured that out, and it's now implemented in all the SAT solvers. But you, well, I didn't figure it out. Like until he showed this to me, I didn't know that this is possible. The trick is very simple. So you don't keep the binary heap updated all the time. So you do sort of lazy updates. What does that mean? Well, it means that when you assign a literal, you don't remove it from the decision heap, because it's of course assigned. You cannot use it as a decision. No, you keep it on there, and only at the situation when you want to get a next decision, an unassigned variable, then you pop maximum score actually from the heap, because of the exponential visits, it's the maximum, until you find a literal which is unassigned, and so you do this lazily, this popping. And that improves actually this whole binary heap usage dramatically. However, still, then when you unassign a literal and it's not on the heap, you need to push it back. And that's an operation which is log n in a number of variables. And this happens actually quite frequently, that you need to push and pop literals on the heap. And this log n really, even though it's only logarithmic, is of course more expensive than sort of the constant time in variable move to front. So it's not completely true, because the search for this for the next literal, like following this next search, is of course not linear. And I even don't have a complexity analysis. Maybe it's in the worst case even like accumulated quadratic, while the EVITS version is guaranteed to be like accumulated, like sort of like n log n, right? But in practice, it's way faster. Okay, so that's what I wanted to show, discuss. This was the second argument. And the third one is, I don't think I have it in the slides. I explained this a little bit in the pragmatics of SAT workshop. So if you want, you can watch that video. So this summer in the pragmatics of SAT workshop, I talked about Chansek's O idea, which is in his thesis, which is I really recommend to read, which is like a split CDCL search into I would call it now actually stable and focused. I think this is the right terminology, but it's not settled yet, mode. And And basically, you want to have SATs over alternate phases. I call it modes because phases are used in a different way, where you sort of focus on sort of stabilizing the search. Okay, and in this case, we would use the VSITs here. This is kind of stable. While this one is extremely aggressive because it really, like, as soon as something is used, it will be picked next, right? While this has actually kind of a low pass filter. And actually what you want to do is you want to have a really high VSITs F here. This F is like 0.9 or even 0.99 for the stable phase, while this thing here, actually, if you would do it with an F, is 0.5, then you can simulate the variable move to front with this n visits, except for this difference. If you want, I can explain this. But this is extremely costly because then you pay really always log n by bubbling these things up. There's no shortcuts. Now, I didn't explain that, but this is good for unsat. And that's good for SAT. And that's really amazing that this is true. So you want to have sort of like stabilized search with a sort of low pass filter on the occurrences of variables in conflicts. That's our EVSITs. And you want to completely turn off the smoothing and be extremely aggressive with this variable move default for unsat clauses. And that's really, this is one of the reasons why our solvers get faster since 2016. So this came first into the Maple solver because the Maple solver had used code from Chan Seok-ho. Okay, I hope this explains this comment by Mate a little bit, but it's really advanced. Sorry about that. Okay, now more basic. So if you're think about a basic CDC loop. So the things we discussed before, it would look like that. So I think this is really code almost you can really take directly and implement. And of course, like it has lots of side effects, which I didn't explain. So the result here is like 0. It doesn't have as a result. And then if you have a global flag, which means like an empty clause was found, then it's 20. That's the encoding of the SAT competition, the exit code of the SAT. So that's why I'm using it here. And if it's SAT, then it's like 10. Otherwise you propagate. So you take the literals which you have not propagated yet. So you find clauses which are unit or empty, and if you find a clause which is empty, you analyze it, you learn a clause and you back jump, and then again usually you would just propagate again, or you in this case unsat. Otherwise, if you propagate it and nothing happens, no empty clause is found, then you check, and that's an interesting part which you might have not realized yet. You simply check dissatisfied here means that all the variables are assigned. If all the variables are assigned, then you can just terminate. That's quite a strong sort of invariant you're using here. Otherwise, because not all variables are assigned, you can pick one. So that's also deterministic then. So you just really can now for sure pick a variable because there's at least one which is not unassigned and everything has been propagated. And that's kind of CDCL in sort of in a simplified way using the things I showed. Okay, however, and I think I mentioned this before, like in the old days, like in CP in the 80s, the people thought about like using sort of conflict-driven backjumping, I would call it. So without learning, so they would not learn the clause. So they would learn kind of a no-good. They would still learn, but they would immediately throw it away. And the reason for that was in these papers which predated the Shaw's paper was because they thought if you would have like sort of this search and you need like many leaves, right? Then keeping all these no-goods would be really bad. The other reason they, like in the CP community, they didn't come up with this idea of keeping the learned clauses was because these constraints, these clauses one would learn, they would be very strange from a from a CP perspective, because they would all look like, you see, like x1 equal, not equal a certain like constant c1, or and so on, right? And that's a strange constraint you would want to keep around in CP, because it's like different from the constraints you would have in the input. But however, in our setting, it's of course completely clear, because we're just having sort of Boolean variables, and this is just another clause. So that's like one reason why SAT is kind of in certain situations better than CP, because it's like very natural to keep those no goods as in the same data structure as you have the input. However, there's the other argument they had is still valid. So you will learn like lots of these guys, and if you just keep all of them, you will just slow down the solver dramatically. Actually, I submitted 3 solvers to the SAT competition which didn't do this reduce what we're discussing here, and it's really bad. So only like in 2004 or something, I figured, okay, so I have to do this, implement this too. Okay, Minisat and also Grasp before they did the following. So they learn clauses, and then they once in a while they would put a limit, like I'm learning 10,000 clauses, and then if you reach 10,000 clauses, you throw away half of them. That was the idea. But then this would make sort of, in particular on the restarts, which we also discussed, then would make the solver incomplete, the algorithm, and therefore they said, okay, so I need to increase this interval. So let us increase it geometrically. So actually what they did had, I think like the first Minisat had like 10,000 K for the first 10,000 conflicts. Then you throw away 5,000 clauses, you remain 5,000 left. And then the next limit would be 15K, so 50% more. Okay, and then when you reach that, you get to 7.5K. And then the next limit would be 50% of that, which I cannot do in my head. Oh, it's like 20.25, right? Okay. Okay, so this was kind of the way how in Minisat in the old days they did the reduction, this geometrically increasing interval. It was still unclear how to which clauses to throw away. Like how do you get like this thing here? Like which of the 50% of the clauses you throw away? And yeah, they introduced something like activity of clauses, and yeah, Kuldeep and Mate are both here. They have this paper on crystal ball, which just tries to sort of figure out what are the best clauses to keep. But we can discuss this maybe down here. But the first thing I wanted to argue here is this was in the old days, and it's in a certain sense still bad if you think about it, because it's still growing like almost exponentially the size of this thing. And what's way better, and this happened with this kind of important paper here, is like figuring out a better metric for the clauses to keep. And if you have a better metric, which is this glucose level, then you can go from this geometrically to this arithmetically increase. So currently it's like you start maybe with 10,000 clauses, so also way smaller than that one. And then every time so you get with like 1K, you do plus 300, then you have 1,300. Sorry, 1. And you throw away half of it, so you only have 500 left. But then here you have, well, 650 left. Okay, and now comes the crucial part. You again do this fixed increase to 1,600, right? And then again an increase of 300 to 1,900. So this throws away clauses, of course, way more aggressively, right? Because the frequency, how this happens, right? The frequency from here to here is way faster than here, which here the frequency also goes up exponentially, while here it's like kind of a square root thing actually. And you only sort of allowed to do this because they have a way better prediction of which clauses to keep, like which like from getting from 1K to 500K, which clauses to throw away. And okay, and I'll just show this again in my minimization example. So the first UIP clause here, sorry, this one, this has called an LBD of, well, now there's like an off by 1 potential error, but actually they would call it LBD of 2. So I checked this, and and then you can, so it's not really the number of, you see, you could think of how many numbers are there, right? This could be the how many levels. And it's 3, like it's 1, 2, and 4. But that's not the ALBD, and so the why. So they would think of this. Okay, so when you backtrack, when you do this back jump, then the S will be flipped, right? And then actually this thing here will become 2, and then the LBD would be actually 2, right? Okay, so that's like a one off by 1 issue, which, yeah, so people who implement SAT solvers, so Matti can check how he did it, but there's an easy sort of like an off by 1 issue here, where you could either have 2 or 3, but sort of the more official version is to have call this clause have an LBD of 2. Yeah, if you now go to the other one, like this one, you see, like here the number is a number of levels is 4, right? Like 1, 2, 3, 4. And the LBD, because of this off by 1 thing, is actually 3. It's still larger than the previous one. So this first UIP scheme guarantees you to learn a smaller LBD, like a level blocked distribution or something is called. But you can think of it just as the number of levels in this clause. And this is a very good prediction for the usefulness of a clause. You want to have this as small as possible, right? So binary clauses by definition have an LBD of 1. Sorry, they would even have, yeah. And all right.
Armin, there are
Yes.
2 quick questions.
Yes.
One is, if you do Luby restarts, the solver is always complete, even with close deletion.
Yes.
And the other question was, don't the levels become irrelevant as soon as you restart? How can you use them to rank clauses?
No, okay. So the reason why these are still good, these prediction, is because they're, let me go, where do I have the picture now? Here. Because you proved in the past that this clause can propagate with, like this one here can propagate with 3 literals assigned, like D, G, and L, while this clause here can propagate with 2 literals assigned, like D and G. And therefore, this clause is better. So you kind of know that from past experience that it's possible to, like with the rest of the formula, that this clause almost behaves like a ternary clause, even though it's a larger clause, right? And this was the question with the restart. So it's kind of not completely true, of course, but it's like, this is the experience. Then you can maybe even figure out during the run that these levels here are improving, right? Maybe you figure out that this clause you during conflict analysis figures out it has a clue level of 3, but then during propagation at one point you figure out, oh, I only have 2 levels in the clause. So the clue should actually be smaller, and that's, well, I call it promoting. I'm not sure like the others call it also promoting. Then you promote this clause from LBD, sorry, LBD 2, 3 to 2. But then it's becoming more important. So this is the reason why this is a very good prediction, actually, I think. However, it's this was already in the original paper. Like they had plots. So you check out this paper; it's interesting because it also tells you something about like how to do research in this domain. They had here the LBD, okay, and then here something like, for instance, usefulness, and usefulness could be used in another conflict analysis, and then this goes really exponentially down. And you could even say that for these two here, like 90% of the time, you only use clauses of LBD2. And this kind of triggered their trick, which is very important, is that just keep all the clauses which have LBD2. Here, this line here. This is kind of the first reason why they can be so aggressive. They're not really removing 50% here, but they first, before they remove 50%, they keep for sure all the clauses which have actually glucose level 2 is the magic number. If you do this off by one thing right, otherwise you need to do 3 right. Okay, and then Chansek also in his thesis came out with, okay, maybe there's another, like, you see, if you look at my picture here, maybe there's another issue here. Maybe this is the second tier, I think you say, and this is the third tier. So you always keep here the first one, right? The first tier is always kept. Tier. And these guys are our low clue. Then those guys are kind of maybe important, but not far less important than these 90%. So, but we keep them around for longer. And these guys we always throw away. So this is like also Chansik. Oh, I'm not sure why. Oh, it's here. Yeah, this should be to the right. And that's kind of the current state of the art. So it's like the first observation was this 90%. So you should really keep those low clue clauses forever. And then you only do the 50% reduction on the others. And then Chansik had this, okay, so maybe we want to split this into 3 parts here. And by the way, this line here is 6. Yes.
To me, it is a bit counterintuitive why conflict clauses with low LBD should be useful more.
So the point is, so first of all, and that's, I also tried this, you could also try throwing away all the clauses, but it really is the case that in CDCL, these learned clauses somehow act as a cache. Like it's similar, yeah, some of you are working on sharp SAT, right? So where you also have a cache for, like in the Ocean sharp subset, where you have a cache for like something what happened before, okay? But in CDCL, so where this cache is sort of less clear how it works. But these core clauses actually give you this sort of caching. So that means like in the future, you will get into a similar situation. And because you learned something about the situation before, you should actually, you kind of traverse that new search space faster. Now the question is, which of the things you learn are useful in this sense? And of course, things which, this was the original motivations in the sort of 90s, yeah, short clauses are good, right? Short clauses, because they propagate fast. However, in the learned clauses, it turns out sometimes they're like clauses with 10,000 literals, which have a clue of 2. And you should keep them because they're useful, right? Because they act almost like a binary clause, right? Because if you know that the clause has a clue 2, it's like almost like a ternary clause. If it has a clue 1, it's almost like a binary clause. So you should kind of keep those clauses which are almost like binary ternary clauses around for later, because they have a high chance to be useful in this caching sense. While the others are less useful, because if you have a clause of clue 10, right, you need to sort of get really the right decisions in a similar way to make this clause propagate. And if this clause is not propagated, it cannot contribute to cut the search space down. Okay. Yeah, here I added one line at the bottom, which is which is new in Catechol and in in KeyStat. So I actually didn't check whether if Mate is also doing that, but it's very important. So there are like a couple of preprocessing techniques, which I feel we won't have time to talk about today unless we skip the source code thing, or where you learn lots of binary clauses. Actually, the reason why lots is not exponential, but it's like quadratic. And in practice, you get these quadratic number of clauses actually. And these clauses are also redundant because they're implied by the formula. But you don't really want to treat them as LBD, say, one clauses, because you can sort of relearn them, and they're kind of less important as these things you learn through sort of this CDCL process. And that's why you should distinguish them from the other learned or redundant clauses. And I use a bit for that. In KeyStat, that's actually pretty complicated because the clauses are not really memory, but only in the occurrence list. And those are really aggressively thrown away. So actually, if they were not used since the last time a reduction was done, I throw them away. And that's, I think, a pretty cool trick, which took me also, I would say, 10 years to come up with, even though now in retrospective, it seems simple. So I think this is the state of the art in reduction. Then restarts were already mentioned, and this is also very important. And so this stable phase here has almost no restarts. And this one here for like sort of every second conflict. And it's also completely counterintuitive. So that means if you want to satisfy formulas, you should not restart often. While if you want to falsify formulas, you should restart like almost every second or third conflict. And the reason for that is that these restarts have been around for quite some time. Like, I don't have the citation here, but there's like a 99 paper, I think. And they were meant originally in the context of local search or Monte Carlo, if you want, because you kind of have this long tail behavior, and maybe there's a solution somewhere else, and therefore you should restart. And at least this completely makes sense if you think about local search, where you're after satisfiable instances, but it's not what current solvers do in like CDCL solvers. It's the opposite. We do the opposite. So for satisfiable instances, we delay restarts. Actually, I would do a Luby style restarts for the stable phase, while I think the Maple solvers, at least like Chan6O solver, would not do any restart in the stable phase. And then in the focus, you restart almost every conflict. I also have like more intuition about that, but so if you're interested, we can reiterate this later. There's like one also like by the two Clocos authors, Laurent Simon and Gilles Autmar, something where they measured the exponential average. And but before that, I skipped the Luby. This is the Luby explanation, which I want to skip. So let me explain the exponential moving average thing, because this is newer. So the exponential moving average idea is from the two my French colleagues, but like we made a simpler version out of it, and it's best explained with this picture here. So this is an instance run up to 50,000 conflicts. I don't see it because my window, 50,000 conflicts. So on the Y, on the X-axis vertical, it's the number of conflicts. So you can think of this as time. On the Y-axis, we have the LBD. So what you actually see are these bubbles here. These are the LBDs learned of the learned clauses, okay? Like here, like a couple of them have like an LBD of 835. And the LBD is, of course, a lower bound on the size. So size might be way bigger or like in the same range, you don't know. And what's good, of course, is this phase around like 30,000, where the LBD is rather small and compact. So that's what you want, right? Right? If all your clauses stay sort of in this regime, then you'll terminate fast. So that's your goal. But these situations where you sort of have really large one, they're bad. Okay, now what did they do? Well, they measure the average exponential moving average of all the LBDs, and there's like one which is this green line here, which computes exponential average with a large window. So I always so when I first learned about this, I made the connection to stock market analysis, right? So you know this, that they usually have this sort of like 9-day window or 6-day window versus like 28 days window. And they do actually the same. So they would also measure the red thing would be sort of the 9-day window of the stock. And the green one would be the 28-day window. And right. And if you're above with the low one, well, then you're going to buy. And if you're below, you're going to sell. And the same criteria we now using for restarts. So if we above, like if sort of my average low window, fast moving average is higher, like here, than the slow moving average, then yeah, my bubbles are too high. I should restart. And these gray lines are the restart decisions. Okay, but while it's the opposite, so my fast moving average here, this one here, is below the green one with a margin like 25%, then I'm doing fine. So I should not restart, like here too. Like the window of the red one is 25, below 25, below this margin. So I didn't draw the margin. Okay, so this is a dynamic scheme for sort of preventing restarts. And that's used in the focused phase, focused mode, and that's very useful. Okay. Yeah, so I think I'm running out of time for the second session, and I'll have here for the phase saving and something to explain in particular, since we're having a post paper. So there's like a whole 30-minute talk on video on sort of the latest thing about that. So I will highly recommend that, but I think I should skip that now. So those interested in phase saving, in what should I forward to this video from the post. Okay, anyhow, so this gives me then kind of this CDC loop with reduce and restart. But this is kind of almost the actual code from from 2018, from Catico. Yeah, this is the standard part. Then here, this thing here, this is just like for printing verbose output. Iteration means you learn the unit through CDCL. And these units are, of course, really useful because they really shrink the formula. If you learn a unit, then you can simplify the formula, and you might trigger additional in processing. And further, it's kind of something, if you would also log sort of binary clause learning, internal clause learning, then what you really see often in CDCL is that you have a frequency of learning ternary clauses, and then this frequency goes up, then you learn a binary clause, okay? And then again, ternary clauses, the frequency go up, the binary clause, okay? So if you focus on the binary clause, the same thing happens. So we do binary clause, the frequency of binary clauses, and then we learn a unit. However, the frequency for binary clauses, if you would plot that in the output of the solver, this would just be too many. And that's why I'm not plotting it, but I'm plotting sort of whenever there's like, you learn a unit. Also note, in the output of the solver, this will be a little lowercase I for iterate. That, of course, when you learn a unit, this unit might imply a lot of other units. So So when you learn one unit, maybe 10 other or hundreds or maybe thousands of other literals become assigned at the root level. And that's why that's a very important sort of like a metric to show. And that's why you have a separate line. You have the satisfies check, then search limits hit. So you can put the solver into a mode where it stops after 10,000 conflicts, for instance. You want to terminate it asynchrony. This was this interrupt API in the IP Acer for SAT solvers. We saw the restarting briefly, the refacing. As I said, this is the POS 20 talk. Reducing, we discussed. Probing, we didn't discuss it all yet, and subsumption, elimination, these are kind of pre-processing. And this one is also a pre-processing, which kind of keeps the working set size small, but it's like puts like I would put here working set as a thing. I think there are no papers on this. I don't recall having seen the papers on this, but it's implemented in many more advanced solvers. So this one here is actually disabled, but I put it here because there's like an ATVA 19 paper. Okay. Then to watch literals are very important, and I can also spend like probably 2 hours on things of like on details of that, but I want to skip that too. Then there's like a parallel SAT, and I only have these lines. And maybe for those of you interested, let me just go briefly over this. Maybe you have a question on that one. So first of all, what parallel hardware we are looking at? Well, they're like vector Unix, like AVX, then GPUs, multi-core, cluster in cloud. I would say the only thing we kind of somewhat understand is this multi-core. Not completely, but this is the only thing we can currently really do. The rest is open. Then, yeah, I mean, like on the cluster in the cloud, this part here is also possible. So you just have like lots of parallel queries. Then of course you can run them in parallel. Then on the cluster is this guiding path principle, which almost nobody's doing nowadays. The main thing which is on here or working on the multi-core is this portfolio. There's some current cube and conquer, but this is specialized for hard, specialized algorithms for hard combinatorial problems. And there it works, but not for the day-to-day SAT solver usage. But if you have a hard problem, like some combinatorial, then you would go for that one. And that actually works on cluster and clouds. The main thing why we don't really have much here, and here is that we're having like in the SAT CDC solver, there's a control dominated sort of algorithms, and while these sort of low level parallelization, really you need some data flow parallelism, and we don't have that in the SAT solver. We don't have any algorithms, so this is a nice open challenge to work on. Okay, so that concludes this session, like a little bit late, I think. Then we need to decide for the next session whether we're going to do code review and source code, which I would very much prefer, or explain the pre-processing part, which is, so you can decide. So maybe we do a poll in Discord and then we can decide on that. All right. Are there immediate questions?
Yes. Hello.
Yes.
Yeah, I have a question. Okay, so I have a question that in the case of you just talking about stability and non-stable phase, and then there is a phase saving, and then there's a non-chronological order. Some of these things appears to me are anti each other. Like for example, if you want to flip your phases, that means not stable. So how this all works together, and what is the crux of understanding here? Like, what can you, like, how to understand this? Like, I see a lot of heuristics one after another, but
Yeah.
how they all work together.
Yeah, I mean, this is the whole thing about SAT solving. So you're kind of exploring things. You see, like this issue with the restart is completely counterintuitive. It took like probably 20, no, not 20, but probably 13, 14 years to figure out that for unsat, you want to do extremely fast restarts, while for SAT, you don't. But now sort of like after sort of we went through this empirical sort of exploration, now I start to develop an intuition why this could be true. But of course, we don't have any proofs. There are no proofs around it. And the same thing is probably true for these phases. So it's completely clear that you want to have split. For me now, intuition is completely clear. So I've seen this work by Chanseok long time ago, but I was not like convinced. But now, sort of after playing with his ideas, I think he's right. So you want to split the solver in these two sort of like things, like this stable and this unstable. Yeah, and then there's this rephasing, which is in this post workshop, which I didn't explain here. So rephasing means you're once in a while, yeah, and I also didn't explain phase saving, but if you have phase saving, you kind of remember the phase you assigned a variable last, and then when you do a decision, you pick this last one. So rephasing completely destroys these, and people have not been doing it before until last year and this year, but it's really useful. And you can even use the local search solver to find sort of better phases. And but it seems you want to being extremely aggressive here, and sort of always trying to sort of to be always saving the phase is not good, and also like the opposite, sort of completely like scrambling the phases once in a while is also not good. So in AI, there's like this in search, like, I mean, this is something they had in CP community for a long time. They had this okay, I cannot write, intensification and diversification. And this is really useful. So if you're thinking about Monte Carlo tree search, MC Monte Carlo tree, MC, what is it? MC, somebody help me. Monte Carlo tree search, probably this, no, which is like used in AlphaGo and others. They have a very similar thing where sort of just once in a while you pick something you should have not explored. And they even have a theory on this stuff. So we don't have any theory in SAT on this stuff, and nobody was able to, like, this is an open question how to apply this to SAT. But these two things, these are really, they're true. So you want to intensify search, but you also want to diversify. And finding the right balance there is kind of doing this engineering-wise is tricky and needs lots of engineering. And then you can develop intuitions. We are far from proofs here. Also with this Monte Carlo tree search, there's like this rule of something. Yeah, I don't know. Yeah. Okay, does this somehow answer the question? If you want to know more about that, really just check out this the video.
Yeah, somehow. Yeah.
Video from.
Oh yeah, thanks for the link. Yeah.
Okay.
So
maybe we can move to the Discord chat rooms and then reconvene back in half an hour.
Yep, let's do that.
Yeah. Okay. So see you all in the Discord rooms.